this camp here. So I'll try to check back periodically to see if I have questions while I'm going through the camps. I mean, otherwise, still if you have questions, just type them in the chat. I think we have a few people here that may be able to answer your questions. That would be Elliot and Liz. Okay. Alrighty, so it's now 9 o'clock. Good morning again, everybody. And my name's Ashton, and I am a peer tutoring specialist at UTD. So, you know, thankfully we'll be back in person this semester. So if you come by the peer tutoring center, you'll see me there. So today for this first camp, let's see, let's start. So today, I'm going to be giving an introduction basically on vectors. That's cool. It's kind of noise down here. So I'm going to be giving basically an introduction to vectors. For those who are taking physics this semester, this will basically be the first, I guess, concept you're introduced to. If you're not taking physics, you may or may not be taking some math class, and in your math classes, you'll have to deal with vectors as well. So a lot of this will apply there. So either way, if you're in physics or not in physics, or if you're in just some math classes, this should be helpful. All right, let's make sure my pen works. So let's make sure that works. Okay. So the first thing I want to talk about basically is just, what is a vector and how we visualize a vector, and what do we even use it for? Um, and so the best way to kind of understand something is let's, compare it to something else. And usually when you learn about vectors, we learn about scalars at the same time. So there's vectors, right? And there's scalars. So this is the right slide. I said this guy, excuse me, supposed to be on this slide. So we're talking about vectors and scalars. So a scalar is basically just a quantity that has only a magnitude, or it just has a number associated with it. And the examples I have here are basically time. And so time would be like, let's say 60 seconds. And so by magnitude, I mean, it just has a certain amount, right? So 60 seconds is just a certain amount. It doesn't necessarily have a direction like a vector does. A vector has a direction. So another example would be like mass. And so, like mass would be let's say like 6 kilograms would be like an example of mass. And again, it's just a certain amount, right? It doesn't have necessarily a direction associated with it. And then the last example I have is just temperature, so like 33 degrees. And again, that's also just a number with no direction associated with it. And so how that kind of compares to a vector is a vector, a vector has a magnitude and a direction. So it has a magnitude and a direction. So this is kind of what we'll be focusing on today, the next hour, hour and a half or so. And I have some examples here for, vectors, which would be displacement. And if you don't know what displacement is, I'm going to describe it in a moment, but just kind of know in your mind that displacement is a vector. Velocity, which you're probably familiar with, is a vector. Acceleration would be a vector, and force would be a vector. So why are these vectors? So velocity is a vector because you can say something like you're driving on a highway at 50 miles per hour or something like that. Right? And then somebody else may ask you, well, you're going 50 miles an hour, but are you going, north or are you going south, right? Because which way you're going is basically very important when you're talking about something like velocity. Because if you're going the wrong way, then yeah, it's not the same as going the right way. So you say 50 miles per hour, south, 75 south or something. So it has a certain direction with its magnitude. And so basically 50 miles per hour south will not be the same as 50 miles per hour going north, right? And kind of that same logic applies for acceleration as well as force. You can be accelerating in a certain direction, and there can be a certain amount of force in a certain direction. All right, so like for force, which we'll talk about forces tomorrow morning, um, a force has a certain magnitude. Let's say we have this box here, all right, and we want to push it. So we apply a force to the right so that the box will move to the right. So basically all that to say that vectors have a certain magnitude, which basically tells you how much. Magnitude is basically how much in a direction is, kind of as it says, it's just the direction that the vector is in. But I'm gonna say it's the angle, because usually we use an angle to kind of indicate the direction of the vector. So you'll see what I mean in this slide here. Let's see if I can erase all that. So there's two ways we can describe a vector. And this is how we visualize vectors as well. We just use an arrow to represent a vector. Get my pen back. So we use arrows like this to indicate a vector. So like this one is pointing to the left at some angle, and this other one, this blue one, is pointing to the right at a higher angle. So that's just how we draw vectors. I guess another thing I should say is, as far as notation, go to the previous slide. So as far as notation, so let's look at velocity. We usually represent that with a v. And to indicate that it's a vector, we put a bar on the top. And so this is the velocity vector. Similarly, acceleration, which we use a to represent that, we put a line up. That shows us that it's also a vector. Similarly, force, draw a line on top, and that indicates that it's also a vector. Whereas scalars or regular numbers like time, you use t, doesn't have a line on the top, mass, or temperature. So notice how these do not have those bars on the top because they're not vectors. Okay. So again, the magnitude. So when looking at this picture, the magnitude is basically how long this vector is. So if I draw these lines here, that shows us how long that arrow is. So that's the magnitude. And let's say that arrow, let's call it vector A with a line on top, right? Well, you may see it with the arrow on the top, or you may see it bold. But for the most part, I'm just going to use the line on the top. So this is our vector A here, indicated by A with this line on the top. And so the magnitude, again, is basically how long it is. So if it's short, it's going to be a small magnitude. If it's long, it's a bigger magnitude. And how we notate the magnitude is, so we use A with the line on top. Now we put these bars on the outside. So this is how we represent the magnitude. So far, I'm just talking about notation and just trying to make sure you're on the same page before we get any further into this, right? So how long it is what we call the magnitude or how much, and we indicate that with the vector symbol with the line on top and bars on both sides. Okay, and then the direction, I said earlier, is basically the angle, right? So in order to get an angle down, we need, let's see a different color here, let's use green. We need to set a coordinate system down. So the coordinate system you're probably familiar with is just the x and y plane. So this is the x direction, right? One up here is the y direction. So I drew it so that let's say the base of the vector here is kind of at the origin. And so the direction is going to be this angle here. All right. So when it comes to measuring this direction, we always start from the x-axis here. We start from here, and then we basically draw our angle to wherever the vector is. So you see this vector is probably at an angle of something more than 90 degrees. Let's say like 150. All right. So this is basically one way we can describe a vector. We can describe it with its magnitude and its angle. So with the magnitude and angle, that would be like all the information you need to describe a vector. And so the other way we can describe a vector is with its something we call its components. So looking at this blue vector now, let's call that vector B. Switch colors. So let's call this vector B. All right, put a bar on the top. So for this vector, instead of describing it by how long it is, but instead of describing it by how long it is, let's describe it using this coordinate system here. So put another coordinate system down. This is the x direction, this is the y direction, right? So another way we can describe this vector is we can use, like I said, the components. So you might be asking, what are the components then? So the components are basically just the coordinates to where the vector is pointing to. So the vector is pointing here. So the coordinates of this vector would be, however far this is and however high up it goes, right? So for example, this could be like, let's say 5, 5, 5, comma 5, right? And so basically this first 5 tells you to go 5 in the x direction. The second 5 tells you to go 5 in the y direction. So we call these here the components of the B vector. So this is how we would write that. And the first 5 we call the x component. So down here, this is B. I put a little x next to it, right? Because this represents the x component. And then going up here, this is by, because that's our y component. So bx is 5, and by is also 5. So those are our components of this B vector. So those are the two ways we can describe a vector, either with its components on a coordinate system, so 5, 5, or we can use its magnitude and direction to describe. Okay. So far, so good. And so now, just to kind of see if you guys are awake, I kind of have just a quick multiple choice. I give you guys a few minutes to answer it, and you can just type your answers in the chat. Basically, I got vector A, B, C, and D on the left here. There should be bars on the top, right? Vector A, B, C, and D. So vector A is 3, 4, and basically I just want you to match it up with its visual representation over here. And let me make these arrows a little bigger. So again, I just want you to match up these vectors here on the left. So A, B, C, and D with 1, 2, 3, and 4. So I'm gonna do one, just to kind of give an example. I'm gonna do D. So D here says the D vector is 0, 9. So 0 in the X direction, and it goes 9 in the Y direction. So this one seems like it's just gonna be a straight line going upwards. It looks like that's supposed to go best with 3 here. So I would say D goes to 3. Simply just because I know this isn't a straight line. I think it's supposed to be more straight than that. It's supposed to be a straight line. Right. So that's obviously 0, 9, right? Because it's 0 in the X direction and it goes straight up in the Y direction. Okay. I think my vectors here got mixed up on the slide too. So let me answer the other ones. So let's look at 3, 4 then. So 3 to the right and then 4 up. I think the closest one that matches with is 4, right? 1, 6. I see. So I think I made a mistake here with this slide. So let's ignore 1, 6, because none of them really match that. But if you look at vector C, it's negative 10, 1. So negative 10 to the left, and it goes down by 1. Looks like that one matches best with number 1. Okay, so not bad, right? So all we did here is basically just kind of match up these coordinates with these arrows that we call vectors. And I might have made a mistake, so ignore B. Alright, so that's not so bad. So let's see now. So now I kind of want to focus on just how do we find the components of a vector. So let's say we're given the magnitude. So if I draw again our coordinate system, and again, most of the time, whenever you're introduced to a problem, you want to draw your picture first. And part of drawing your picture is putting down a coordinate system. So you always want to do that first. So let's say we have this vector, right? And we want to find its components. So they give us, we're given the angle, and we're also given the magnitude. Let's call it vector A. So if you're given an angle and a magnitude, how can you find the components of this vector? Where the components are, you know, the placement of where it's at on the xy plane, right? So if we look at this, kind of take a step back from what I've been saying so far, this obviously makes a right triangle. Now, this here is a right triangle. And so automatically when you think right triangle, you probably think, well, Sohcahtoa, right? So that's what we're going to use here. Sohcahtoa, right? Where so is basically sine of the opposite over the hypotenuse. So, alright, and so on and so on. Cosine adjacent over hypotenuse and tangent opposite over adjacent. I'm sure you probably have heard that. If you haven't, I'm sure you can maybe pick up on the pattern here, where O is opposite and H is for hypotenuse, and A is for adjacent. Okay, so we're trying to find the components, right? So let me label that. Let's use a different color. So we're trying to find this x component of A. So AX and AY here. So that's what we're trying to find. So we have this vector A, and we're trying to find these x and y components. Okay. And let's say we're given the magnitude and the angle. And we're trying to find these. Okay. So, like I said, we're going to be using Sohcahtoa. So let's just, apply these labelings I have in our right triangle into the Sohcahtoa. So let's start with sine theta. So if we say sine theta of this triangle, sine theta is going to be equal to the opposite, right? So the opposite of this angle is AY, right? Okay. So it's going to be AY, the y component of A, divided by the hypotenuse, which is just the magnitude. Okay. Okay. So now, again, we're trying to solve for the components, right? So let me also do cosine. So cosine theta is adjacent. The adjacent side is the x component. Again, divided by the hypotenuse. And lastly, I'm going to write down tangent theta, which is the opposite, AY, over the adjacent. Okay. So now, at this point, we can solve for our x and our y components, the y and x components, because we're given here the magnitude and the angle. And we're going to do some examples with numbers so that it kind of clicks a little better. But real quick, so we can see here then that the y component then is given by the magnitude of the vector times the sine of the angle. The x component similarly is given by the magnitude times cosine theta. Okay. And then you might think, well, what do we use tangent for? because we use sine to solve for the y component, cosine to solve for the x component. So what would tangent be useful for? Well, if we kind of look at tangent here, it gives us both the ax and the ay, or both components in it. So you may not really know automatically what that would be good for, but just to kind of say it here and now, because we're going to use it later, is you most of the time use tangent to solve for the angle. Even though here we don't have to solve the angle because it's given. But let's say I want to solve for that angle. So to get rid of the tangent, I do arctangent on both sides. So it's tangent with the -1, ay over ax. Okay, so this here is basically the kind of the very beginning of really dealing with vectors. So we can solve for our y component and our x component with just the magnitude and the angle with just these two things. Okay, so let's do some examples then. Let's see what we got here. So let's start with this. So we want to find components. Let me write that. Oops. So we want to find the components. So let's call this vector D. Call this vector D. So we want to find dx and dy. Right? So this is our vector D. Let's start by putting our coordinate system down. Okay. So when we put our coordinate system down, since the coordinate system is arbitrary, which basically means arbitrary basically means you can kind of set it wherever you want it to be. So I'm always going to set the coordinate system at the base, where the base is kind of the bottom of the vector here. Or we usually call it the tail. We use the right language. Call it the tail. I'm call it the arrow side, the head. So I always put the coordinate system, the origin of the coordinate system, at the tail of the vector. Okay. And let's say, we're given the magnitude. Let's say it's 10. And let's say it's 10 meters to give it units as well. And let's call this angle, let's say it's 190. Looks about 190. Okay. We know that the length or the magnitude of this vector is 10, and we know this angle here goes all the way over here is 190. Okay, so we want to find the x and y components. So we want to find this here. This is going to be our x component. This is the x. And then here, going downwards, is our y component, dy. Okay. So let me go back to the last slide just to kind of show you how we found these components with this vector. We basically use Sohcahtoa, we use our trigonometry here to solve for the x and y component. But I guess this one looks a little easier, right? Because the vector angle is a bit smaller. It's not kind of bent all around to the other side. So let's see if I can erase. Yeah. So let's actually do this one real quick because I think this would be easier to start with. So if this magnitude is 5, we got this angle of, let's say, 53. Let's say 30. Pen color is blue. Okay. So this is our vector we're looking at first, and we want to solve for the x and the y component. And the equations I kind of just derived a moment ago look like this. We said the y component is basically the magnitude times sine of the angle, and the x component, magnitude cosine times the angle. Okay. So if we just plug in the given information of this triangle, which is the magnitude is 5. It's a typo. Oh, it shouldn't have been there. So 5 meters. So we have 5 times the sine of the angle, which is 30. And we have 5 times cosine of 30. Okay, so we put that in our calculator. See, that gives us, it's roughly about, sine of 30 is a half, so this is about 2.5. Oops. 2.5 meters. Okay, and the x component, putting that in our calculator, cosine of 30 is square root 3 over 2. So let's see. That's about 4.3. Let's put that in meters. Okay. So from there, that's basically all there is to it. Now we have our x and y components. So we can say, well, vector A is 4.3, because that's the x component, comma 2.5. Okay, so far so good, right? So far, we've talked about vectors, um, and we've talked about how we can describe vectors with their components, or we can describe them with the magnitude and the angle. Um, yeah, so let's do that next example now, because this angle now is more than 180. It goes way over here. And so if we look at our x and y components, which we're trying to solve for here, and just kind of looking at it based off of the graph that it's on, or the coordinate system that it's on, we can see that this dx it must have a negative value, right? Because it's going to the left. And dy must also have a negative value because it's going downwards. And I say that because it's good to keep that in mind once you solve for your answers, because we know our answers should be negative. Okay, so let me write down again these two equations. theta d. So as before, we can say dx is equal to the magnitude times cosine theta dy times sine theta. So these are the same two equations that we had in the previous slide. Here and here. So x got the cosine and y we have with sine. Okay. So we have our equation, so we can really just jump right into it and put in the 10 and the 190. Let's get a different color. So let's see. That's going to be then 10 cosine 190. We also have 10 sine of 190. Alright. So let's put that into our calculators and we'll get something like this. I think it's just negative 9.8 and negative 1.7. Okay. So notice our answers, they're both negative, which was to be expected because of the orientation of the vector. So these answers of negative 9.8 and 1.7 both check out. Okay, cool. So, that's all good and dandy, right? This is basically the same thing we did in the other problem. We used these two equations that we kind of derived from trigonometry, and we use them to solve for the components of this vector, given that we know the magnitude and the angle. So let me do this same problem now a different way, because let's say you did not know these two equations, by heart. You just don't remember them. So you kind of have to break down this vector from scratch. So let me do this problem again, assuming that we don't know these two equations. So kind of starting from scratch. I'm gonna use the same numbers though. So we're given that the magnitude of d is equal to 10 meters, and that the angle is 190 degrees. Okay. And let's put our coordinate system down again. So we got that, got that. Alright, so again, I'm assuming, let's say we don't have these two equations, memorized, which you may not. You don't necessarily need to remember them. We just have to remember that this makes a right triangle. So this small angle here, this makes our right triangle. And I'm gonna call this small angle, I'm gonna call it alpha. And I'm not calling it theta because this whole angle here is theta. And that's equal to 190. Okay. Then you may say, well, what's alpha then? Well, I think it's pretty straightforward to solve for alpha, because we know each one of these quadrants is 90 degrees, or overall, it's 360 because it's a perfect circle. So, well, so we can solve for this small angle then by just subtracting 190 from 180. So we can say alpha equals 190 minus 180. Alright, you kind of see how I got that? Because, half of this circle up here is 180, and that little extra piece has to be subtracted from the 190. So alpha then is 10 degrees. Okay. So then you say, all right, well now I got this small angle of alpha so that I can use my trigonometry, quote unquote. So I can basically look at this triangle and I'm gonna redraw it, but right side up and mirror flipped. So it's a little easier to see. So we're drawing that triangle. So this here that I drew is that same triangle, just kind of flipped around so we can see it a little better. And we know that this bottom part here is going to be our x still. This is dx. Gives us the x component over here is dy. So I'm going to write that over here for ours, dx, dy, and we know the hypotenuse is 10. Okay, so again, we're trying to solve these components, the x and the y. So in your mind, without, in your mind, we got to use trig to solve this, right? So again, we think Sohcahtoa. So we start off with sine theta, or alpha actually. So we're looking at alpha here. Scratch it. This is sine alpha. Sine alpha is going to be the opposite. So dy over the adjacent, opposite over hypotenuse, dy over the hypotenuse. Okay, so then solving for the y component, then we see dy is just going to be the sine of alpha. All right, and let's plug in the numbers we have where alpha is 10, and the hypotenuse is also 10. So if we put that in our calculators, we get 1.7. And that should look familiar to you. So let me do the other one too. Let's do the solve for the x component. So we use cosine alpha equals dx, right? The x component divided by the hypotenuse. So now let's solve for our dx. So dx is going to be hypotenuse times cosine of alpha. Plugging in our numbers, 10 and 10 again, we get that dx is 9.8, which that should also look familiar. Sure. Yeah. And those are both in meters. Get the units in. Meters, centimeters. So for the x component, we got 9.8, and for the y component, we got 1.7. So those are the same numbers that we got a moment ago, right? The only difference is that they're positive values, right? So basically what I'm trying to show you here is that we got the right answer, but now we got to add in the signs because we know the x and y components should both be negative because of, again, how this vector is oriented. So we can just include the negative, just throw it in the negative because, by logical reasoning, we know the actual angle was not 10 degrees. It was actually 190. And the fact that the angle was 190 is what tells us that these numbers should be negative. Cool. So let me kind of recap what I'm trying to show here. Let's see if I can clear all this. There it is. So again, here I'm just trying to show that there was two ways that we can solve for the component here. So the first way we solved for it is we can use the correct given angle of theta here. And if we use this angle of theta, it basically takes care of the signs of our components. So using theta, we get dx dy and 10. Okay, so if magnitude is 10, theta is 190, alpha is 10. So using theta, let's see, cosine 190, that gave us the negative 9.8. This gives us negative 1.7, which is the correct answer, right? And let's say we could have used alpha. So using alpha, I hope y'all can see this blue color. It's a little bright. Okay. So these are the two ways that we could have solved for the components of this vector, right? So basically what I'm trying to show here is there's two ways we could have done it, using the theta given or this alpha here that we kind of solve for. And the differences that I want to point out is that using theta, this angle that starts at the positive y direction, positive x direction, I mean, using theta, using that angle, it automatically takes care of our negative signs because that angle points into the negative quadrant. So that makes sense that does that. Then also kind of notice that, even if we were to use 10 as our angle, this small alpha, it still gives us the right answer, but we have to include the negative sign because we know that the vector is over there. So we have to manually include that. Manually include. Okay. again, I think so far so good. I think just kind of, dealing with these angles might be the most tricky part of, I guess, these vectors and components, right? So let's do another example. And I want to show you kind of multiple ways you can look at these because, knowing how to do it more than one way and seeing the differences between those ways, just kind of gives you a lot of insight and just helps in the overall solving of the problem. So now I've got this vector that's pointed in quadrant 4, right? Excuse me. And we have this angle. So let's call this vector, let's call it C this time. So the magnitude of vector C is, it's 15, and that angle theta is 330. So again, we're still trying to solve for the components. And let's say 15 meters per second. Let's say this is a velocity vector, and that velocity is pointing in that direction. Okay, so again, we want to find the components. So if you've got a pencil and paper with you, I invite you to, kind of walk with me in solving this. It's, I think I spelled that wrong. So again, I'm just taking it a little bit slower this time, just to kind of give you time to, give you a chance to kind of work through it before I kind of get into it. I guess also while you work on it, notice how I wrote this here. Great. So notice how I wrote this here. I wrote this vector C is basically equal to its components in parentheses. All right, so this is how we can like kind of represent a vector. But let me show you what's incorrect. I can't write it this way. I can't say vector C is equal to, I don't know, I can't write it like this. Right? So that would be, an incorrect way of writing it there. Even though we can represent a vector with its magnitude and angle, this is just basically incorrect notation here. So that's wrong, just to say that. But we can say, we can write those separately, but we can't like set them equal like we write it here. So that's just kind of notation. So let's get into the problem now and finding these components. So looking at that vector, we see it's in quadrant 4. So we know that the x component is going to be positive and the y component is going to be negative. So here's our x component, cx, cy. Okay. So I'm going to solve this. I'm going to solve it more than one way. I'm going to solve it 2 ways like I did the last one. Again, to compare and contrast the differences between the ways we can solve it. So let's say, we remember that the x component, most of the time, not always, is associated with cosine. And the y component is most of the time, not always, associated with the sine of the angle. And I say most of the time because I'm going to show an example where this may not be true. But it is fair to say that most of the time the x component is associated with cosine and the y component is associated with sine. But again, it very much depends on your vector and how it's oriented. So for this one, we're just going to plug in the 330, right? And kind of how I said before, this 330, putting in this angle, it should take care of the fact that this cy here is going to be negative. So let's see if that's the case. So just plug in our numbers here. Magnitude is 15, if you're walking along with me. Cosine of 330. Putting it into our calculator. That is, what's that, 12.9? Alright, okay. And our y component is going to be, let's see, putting in the numbers, 15 and sine of 330. And that's meters per second. Never want to forget the units. And it's meters per second because we started with meters per second, right? Okay, and yeah, the y component. Let's see, plugging in 15 sine of 330 gives us negative 7.5. Nice, meters per second. And see, so now, we look at those answers, 12.9 and 7.5. We look at those answers and we think, well, those make sense. All right, those make sense because the y component, pops out a negative number, which is to be expected because it's in the fourth quadrant over here. And if this was drawn to scale a little bit better, you would even see that this x component is way, way longer than the y component. But I didn't draw it to scale here. So, all right, cool. So it's not so bad. Like, all that makes sense. So, what's the fuss about physics being so hard? Um, so again, we're just getting started. All this is just kind of a foundation we're trying to build. And let me now do this same problem, but a different way. All right. So let's say again you don't remember these by heart. These equations. Let's say you don't know those by heart, and so you have to kind of go through the whole process of breaking it down manually, which is nothing wrong with that. It's probably actually even preferable. So, excuse that unstraight line. So that's our theta, and we say, well, I want to use trigonometry on this vector, so I'm probably going to need to use this angle here, right? Interestingly, you also could have looked at it and said, well, what about this angle? So there's kind of three different angles here you can look at. And change colors. There's this small angle, and there's this bigger one on the other side. And this one. So there's three angles. So at most, you know, there's three different ways you can do this problem. And so if you're trying to like compare with another person on how they did it, they might have done it a different way. But each way should work out. So let's use this. Let's use the red angle first. This one right here. Let's call it alpha. Let's call that red angle alpha. All right. And just to say it again, I think we used C. Yeah, C. The magnitude of this angle or this vector is 15. Yeah, I think I used 15 meters per second. And theta was 330. Okay, so if we want to use alpha, then which somebody somewhere probably would have thought to do. First we have to solve for alpha. So if theta is 330, then this last little slice of the pie, if you can see it, is going to be 330 minus, or 360 minus 230, excuse me. This 360 whole circle, right? Minus 330 so we can get that little piece of alpha. And we see alpha is going to be equal to 30. Okay. So we're going to use this angle now. So if we look at our triangle that makes, all right, triangle, and we've got our x and y component. Okay, so now we say, all right, we got our triangle down. I know what alpha is, and now let's redraw it so it's again a little easier to look at. So I just flipped it upside down. And this side over here was the y, and down here was the x. So when you're kind of reorienting your triangle, just be careful to make sure that your sides stay the same when you flip it or invert it. Okay, so again, we're kind of doing this from scratch. Assume we don't remember the equation. So we use trig. So we use Sohcahtoa. And again, I invite you to work this with me. So when you think Sohcahtoa, so sine is opposite over hypotenuse. So opposite is supposed to be alpha, right? Not theta. It's just a habit. Alpha, alright. Okay. So cy is the opposite of the hypotenuse. Okay. So solve cy then. Sine of alpha. Okay. So it's 15 times sine of, we're using alpha, so 30. So put that in our calculator and see what that gives us. And while you do that, cosine of alpha is going to be adjacent over hypotenuse. Okay, so that's cx over the hypotenuse with the magnitude. So cx, the x component is going to be equal to the magnitude times cosine 30. All right. So that's 15 times cosine 30. Okay, so let's put both of those in a calculator, and I think we get, let's see. For y, we get 7.5. All right, expected that, right? Right here. And for the x, we got 12.9. Okay, so far so good, right? We expected both of those numbers, but notice that the y component is positive, but we know it should be negative. And so since we use this angle alpha, we have to manually include the fact that this is negative. Because we can manually include our negative there. And then boom, we got the right answer. Okay. Again, so far so good. That makes sense. So now let's do it using this purple angle. It's the last way. Yeah. So click this. Okay, so now let's see. Okay, so now this time we're gonna use this angle. Let's call it beta. Right. X and Y. So now we're going to use angle beta. So first you would go about solving for what beta is, and just to kind of walk you through that real quick. So over here is 90. Over here is 0. Excuse me. Up here is 90. Up here is 180. And then so down here at the bottom is what, 270, right? And then 360 and so on and so on. Okay, so if this, to down here is 270, and this whole angle is 330, we just have to subtract them then so we can solve for beta. Right, so it's not bad. So beta is going to be 330 minus 270. It's 60. Okay. Beta is 60 degrees. 60 degrees. So far so good. Okay, let me think to yourself, alright, I got my angle here, I got that beta. So now let's look at our triangle that makes. Use a different color. So again, since we're using this angle, we'll kind of look at it. So over here is still our y component. So let's see y over here, right? Let's see x right here. Because this is going in the x direction down here. Over here's the y direction. Put our square there. Okay. So now we take our triangle that we just made with beta. I'm gonna, kind of redraw it over here. This is beta. So notice now, when I use this angle beta, this bottom side is the y component, so it's y. The opposite side is x. Okay. So notice the slight difference here. When we use this angle of beta, the adjacent side is the y component, and the opposite side is the x component. Okay. So now if we do, using our trig and Sohcahtoa and all that, we could say, well, the x component, well, let me write it all out. Say cosine or sine theta. Sine theta is the opposite, so the opposite is the x component, right? Divided by the hypotenuse. So the x component is going to be equal to c sine beta, excuse me, it's beta. Okay. Similarly, cosine beta. So cosine is the adjacent is cy. The hypotenuse, okay, so cy equal to magnitude for the hypotenuse times cosine beta. A little different this time, right? So notice now that the x component is with the sine beta, and the y component is with the cosine beta. And like I said before, most of the time it is the case that x goes with cosine. But this is one of those times where, because we use this angle beta, it basically kind of flipped the sine and cosine. And so let's see if that still gives us the right answer. So we've got 15, and we're using beta now. Beta is 60, so 15 sine of 60. And we've got 15 cosine of 60. Put both of those in your calculator. And it looks like we get 12.9 and 7.5. Cool. So again, we get the answers we expect. So the x component is 12.9 and the y component is 7.5. And notice again, we have to manually include the negative for the y component. Manually include this negative. Okay, so I just did this same problem now 3 times, 3 different ways, and you got the right answer each time. And you will get the right answer each time, as long as you're careful, right? So, now, let me just write all of that out, so we can move on to the next topic. So I just really want you to kind of understand that, there's more than one way to do a problem, and as long as, you take your steps correctly, you're going to get to the right answer. So theta, so using theta, and what about C? C, right? C. And so again, x usually goes with cosine. This one goes with sine theta. So that gave us the right answer. That gave us 12.9. This one gave us negative 7.5. And that was using theta. And we'll use alpha. Alpha was 30. So using alpha. Just so you can kind of see all of these answers next to each other. You know, it kind of makes it, I think, a little bit more clear. And lastly, so when we use beta, notice how it was flipped, the sines and the cosines. Let's cosine beta. Boom. Okay. Okay, so using these three different angles, we get the same answer each time, which is, pretty interesting, right? Because we use different angles, but we got the same answer for the most part. And so notice basically using alpha and beta, the negative is not included here because we have to manually put those negatives in using those angles. Whereas if we just use the angle measured from the positive x direction, it takes care of that for you. Okay, cool to see, right? I just really want to kind of get that down there. All right, so moving on then. So basically what we've just done is just find vector components. And whenever we find vector components, we use trig. So sines and cosines. Okay. And so now let's do this the other way around. For those last couple problems, we were given the magnitude and the angle. No. Yeah, we were given the magnitude and the angle, and we have to find the components. And so now we're going to do this the other way around. We're going to be given the components. And so here we're given some vector s, should be a line right there. Some vector s is 3, negative 4. And we want to find the magnitude and the direction of this vector. Alright, so notice how now we're basically it's flipped the other way. Because before we were given magnitude and direction, and we found the components, but now we're given the components and we're trying to find the magnitude and the direction. Okay. So first, again, we're always going to start off by drawing our picture and our reference frame or coordinate system. So x, y, x, y. Vector s is 3, negative 4, so 3 to the right, negative 4 down, so something like that. Yeah, so our vector is 3 comma negative 4. Okay. And now, well, we're trying to solve for the magnitude. Let's start with that. So the magnitude is how long. It's how long the vector is, all right? And again, excuse me, this vector is always going to make a right triangle. It's always good to notice. It's always good to notice when right triangles are being made. because whenever there's a right triangle being made in any situation, we can use trig, and it just kind of makes things better. Now I guess you might be wondering, why did I go up that way when I also could have gone this way. Just a different color. I also could have said, well, it makes a right triangle right here. Alright, which I guess you would have been right to say that. And so again, now obviously there's two ways we can do this then, right? We could have looked at that right triangle, the purple, or the empty one. And I'm gonna look at the empty one. And I guess I'll do it both ways too, just to show. So I'm gonna look at this empty triangle. So I'll make my little angle there. And I'm gonna call that angle alpha, right? It's not theta, because theta again is always measured from the positive x direction. It goes all the way around. So that there is what theta is. Okay. So again, solving for the magnitude, right? So let's take our triangle and redraw it. It's a little easier to see this. That's alpha. And we have in the x direction 3, alright, and in the y direction it's -4. So it's 3 right here. This side is -4. Okay. So this should click something in your mind somewhere. This is classic here. This is classic, classic what? We're trying to solve for the hypotenuse. Alright, we're trying to solve for the long side, but we're given the other two sides. And yeah, we're given the other two sides, and we're trying to solve the hypotenuse. Give that a second, kind of let that sit, let you that, how do you think you would solve for what the hypotenuse or what the magnitude is? So if you're, still thinking about trigonometry, right? There's another, thing in trig which has probably been repeated to you hundreds, if not thousands of times, is Pythagorean theorem, right? Pythagorean theorem. You always hear about this. Especially it says, the hypotenuse is the sum of both of the sides squared, right? So, Pythagorean theorem, a squared plus b squared is c squared. A squared plus b squared, c squared. All right, very, very classic in, I guess, elementary, right? So, A would be like 3, B would be the 4, and C is the hypotenuse, right? So C is what we're trying to solve for. Well, C is basically this magnitude. Okay, so if we want to solve for C here, then we just say, well, C, the hypotenuse, is the square root of a squared plus b squared. Okay, so then we take this quote-unquote Pythagorean theorem and apply it to our problem. So I'm going to write it down symbolically before I put in the numbers. So the magnitude of S is equal to a square root of the x component squared plus the y component squared, right? All right, boom. So this would be like a I guess, our third equation, or fourth one, depending on how you're counting. Let's just say it's our third one. So it's just like, one just needs to know at the drop of a hat almost. Magnitude is the square root of the component squared, right? Okay, well, let's go ahead and use that for our problem here because we have the x and y components. So we can solve for that magnitude. It's going to be the square root of 3 squared plus 4 squared. I ignored the negative for 4 because if you square it, the negative is going to drop out. So I didn't even bother to write it. But I will write it just to be precise. It's negative 4. But it's squared, so it doesn't really matter. All right, so we square both of those, add them up, square root it, put that in your calculator, and we get 5. And let's say 5 meters. Okay, so the magnitude, this is also meters. So the magnitude of this vector here, the magnitude of the vector 3, comma, negative 4 is 5. Okay, not bad, right? So now, what is the direction? So we solve for the magnitude. Magnitude is 5. And yeah, so now we want to solve for the direction. Let's see what time it is. Okay, it's 10:30. So we've got about 20 more minutes here. So let's I'm gonna try to speed up a little bit so I can get through a little bit more information. But I really also want to focus on this next part of finding the direction. Again, because dealing with this angle, finding its direction, just how like before there were multiple angles we could have used, right? The angle, I feel like, kind of confuses people a lot. So I really want to focus on finding the direction of this vector here. But I think I've set it up pretty good so that you'll, understand this. So we're trying to solve for the direction, which is theta, right? So we're trying to solve for this big angle here, the one that goes all the way around and points to the vector. But I guess if you look at the picture I drew here, we're looking at alpha. So it's that small angle alpha. And so let's solve for alpha first. All right, so let me clear this and let's solve for alpha first. So yeah, give me a quick yes or no, or a wave in hand, if this is making sense so far while I wrap this up. What are we doing? Trying to solve for the direction, right? Okay, trying to solve for that direction, right? So again, we're going to use trigonometry for this, and let me write out all of our trig quantities. Oh, actually, I'm just going to jump straight to it because I think I wrote it before. So if you look at in this slide, I might have erased it. Yeah, so I'll write it again. So I think in one of those slides, I wrote something like this. I wrote sine theta, I wrote cosine theta, and then I also wrote tangent theta. That was the one I kind of we didn't use yet. So tangent theta, which is TOA, is opposite over adjacent. And so here, there's an alpha. So tangent alpha is gonna be the opposite, which is -4 over the adjacent, which is 3. Okay. And to solve for that angle alpha, we have to do arctangent or inverse tangent on both sides. Arctangent, intangent, that language is interchangeable, but they mean the same thing. So alpha then is going to be arctangent or inverse tangent of -4, 3. You say, okay, well, that's not bad. Just throw that into the calculator. And once we do that, we get -53. -0.1, yeah, -53.1 degrees. Okay, so notice how, first of all, it gives us a negative answer. Whenever they ask for us to solve for the direction, the answer is never going to be negative. Same goes for the magnitude. The magnitude can never be negative. Right? That's key. The magnitude is never ever negative. The direction, I guess, can technically be negative, but your answer for the direction is never going to be negative because it's always going to be measured from here all the way around here. Right, so the fact that we have a -53, first of all, we know that this small angle here is what's 53, not theta. And the negative just basically takes into the account that it's kind of pointing, it's going in the opposite direction. So that's kind of where that negative pops in, but you can really just ignore that negative for the most part, because we're trying to solve for theta. Okay, so we want that big angle that goes all the way around here. So we can just subtract 360 from 53. 360, right, minus alpha. So basically 360 minus 53.1. And that is 30. I'm just gonna round about 307 degrees. Alrighty then, so now given basically these components, x and y components, we're able to solve for the magnitude, which was 5 meters, and the direction or the angle theta is equal to 307. Okay, so let's do another one now. Okay, so now again, I invite you to, work through this with me or on your own. Actually, I'm gonna let you kind of work through this on your own, and I'm just gonna, write it out, and you kind of just follow along. It's step one. You want to start with your picture. After you draw your picture, Um, you want to basically label your picture, so you want to label the axes, label the x and y components on your vector, and label what the angle theta is. Okay. So I won't be able to get into everything I have prepared here, but yeah, that's actually one more thing I definitely want to talk about after this. So, um, let's do this real quickly then. So, doing this real quick, we got negative 15, 3, so negative 15 to left, 3 upwards, so it probably looks something like this. And we want to find the hypotenuse of this. And so this is negative 15, this right here is 3. And so the hypotenuse then, real straightforward, it should just be the square root of the x component squared plus the y component squared, right? Well, that's just 15 squared plus 3 squared. Alright, I left out the negative here, but no, the negative doesn't matter. And that's going to give us 15.3 meters. Okay, so that's the magnitude. So now what about the angle? What about the angle? So again, the angle starts from positive x direction and goes over like that. That's the angle theta. But for our triangle, we're looking at a smaller angle up in here. That is, let's call it alpha again. Okay, so let's use this, our tangent, where it's opposite, so 3 over the adjacent 15. I throw in the negative, and that gives us 11.3 degrees. Okay, makes sense. So that's supposed to be alpha. Excuse me. This is alpha. So alpha is 11.3 degrees. Makes sense because it's a tiny little angle there. So we want theta, and so to get theta, it's going to be 180 minus alpha. And that's 168.7 degrees. So if you're asking, why I used 180 instead of 360 this time, again, just kind of look at the picture here, right? It makes sense that I use 180 because to go halfway around this coordinate system here, let's go halfway around here. That's 180, right? And if we're trying to solve for this angle up in here, then it makes sense to take 180 and subtract out the alpha, right, so that we can get theta. So that's why I did 180 minus alpha. So it's not always that we're subtracting from 360. Again, it depends on your picture. So that's why it's always kind of important to have your picture so things like this make sense. So we solve for the magnitude, it's 15, and we solve for the direction. So we're good to go. So lastly, I kind of want to talk about vector addition and vector subtraction, because I think this is another thing students tend to have a problem with. Um, but I just kind of want to be very clear and visual here about this. So let's say we have a vector A um, that looks like this. Say it's a 0, comma 3. And so visually, the vector looks like this, just a straight line, right? And let's say we want to add that vector A with vector B. And vector B is, let's say it's 3, comma 0. Right, so visually that vector is just a straight arrow upwards. And so what happens when we add those two vectors together? Alright, so what happens when we add them? So visually, again speaking, when we add up vectors, adding vectors, let me write that here. Actually, no, let's do it on the picture. There's two different ways we can add them as far as visual representation. There's something called the tip to tail method. Tip to tail. So using the tip to tail method, we'll draw our first vector, vector A. So this vector A is right here. Let's see that. And let's say vector B is a different color. Vector B is, so tip to tail basically means we start at the origin. So we started at the origin, right? We drew out vector A. It's just a straight line. And then you start from the tip of A and put it at the tail of B. So B goes like that, right? So this is B. And now down there's A. And so when we add those, it basically gives us something called the resultant. Let's call it vector C. And the resultant vector, we always go back to the, go back to where we started and we draw a line to the new position there. That's vector C. So vector C is equal to, and so when we add them up, as far as numbers are concerned, we add up components. So we add up the x component of A with the x component of B. We add the y component of A with the y component of B. So vector C is going to be 3, 3. Right? And that makes sense even with the picture here, right? Because it basically makes this vector. Okay, so basically vector addition and vector subtraction is kind of the last thing I want to talk about. So I'm going to be wrapping this up in 5 minutes here. So I kind of just want to be real clear about the visual representation of adding up these vectors and subtracting them. So it makes sense, right, that we just add up the components of vector A and B to get this vector C. Okay, so let's do this one here. So here it says find the resultant vector, vector components, magnitude, and direction. So whenever they say the resultant vector, that just means the sum of the two vectors in question here. So this is what we're doing. We're adding A plus B to solve for C. So we're trying to solve for C. We want to find the components of C, we want to find the magnitude of C, and then we want to find the direction of C. So let me draw it out visually first. So A is 3, 4. So A looks something like this. B is 0, 8. So that looks something, 0, 8 looks something like this. So when we put that on our our graph here using the tip-to-tail method. A, just like that, that's A. And then starting at the tip of T, put the tail of B. It goes like this. Okay. And C then, you start back at the beginning of where the first vector was, and then go to the new point there. So that's C. Okay, so visually, this is kind of what's happening. So putting in the numbers and just adding them up. So we've got A is 3 comma 4 plus B, which is 0 comma 8. And again, we add up their components. So we add the X component with the X component, and we add the Y component with the Y component. All right, we just add those up. So 3 plus 0 is 3. 4 plus 8 is 12. Yeah. Oh, wait a minute. So I made a slight mistake. B actually goes straight up like this, right? Mix that up. B goes straight up like that. It's 0, 8. So it's a straight line upwards. So that. So B is a straight line upwards. So B goes like that, then C looks like this. There we go. Okay, so 4 plus 8, 12. So that's the components of C. All right, and so now that makes sense with the picture here. 3, 12. So 1, 2, 3, then it goes 12 all the way up there. So that makes sense. So we have the components now. We have the components of the resultant vector. It's 3, 12. So now let's solve for the magnitude. Real quickly, right? It's going to be the square root of 3 squared plus 12 squared. Right? Just square the components, add them up, then take the square root. And that gives us, putting that into our calculator, that gives us roughly about 12.4. Okay. Okay, again, I think that's a solid answer, right? It's positive. Again, the magnitude is always going to be positive. And then lastly, we want to find the direction of C. So the direction of C is the angle, right? So that's going to be, this angle here, that angle. Okay, so that's pretty straightforward this time, right? Let me draw that again so we can see it a little better. Let's see. So that's off of that angle, right? So no component, so we know this is 3, this here is 12. So using arctangent, it's going to be the opposite of the angle, opposite which is 12 over the adjacent 3, opposite over total, yeah. And let's see what that gives us. Looks like that's about 76 degrees. Rounding up. Okay, that answer looks good. So now we basically solve for the direction, solve for the magnitude, and we found those from the addition of the A and B vector. Okay, so I'm just gonna end it there then. Wish I could go further. I guess I kind of underestimated how much I would talk, but I think this is a good introduction to vectors. Um, vectors basically just deals with a lot of trig, a lot of angles and whatnot, and just a lot of visual representation. If you understand visually what's going on, I think it helps, with the math and whatnot. This is my last question. I'll let you guys kind of work on this on your own, but I'll draw it out visually, and I think, the math will kind of just fall into place. And with this question, this is going to wrap it up for today. Um, as far as the physics portion of the camp. So let's see what we got here. E is negative 2, 9, so negative 2, 9. That point's like down here, right? And then F is 4, negative 4. Let's change colors. 4, negative 4, 4, negative 4, so 4 that way, then down. Alright. So tip to tail method. This kind of goes down this way. So adding those two up, so E plus F to equals G. G looks like this. So start here and go all the way down, and then that's G. Cool. So, same as before, if you're working on this, what are the components of G? So there's an X component for G, there's a Y component for G. So what are those? Then what's the magnitude of G? All right, and then you have to solve that magnitude. It's going to be the component squared. And lastly, what is the direction of G? So what is the angle? What is this angle? And I might take a little extra thought there, so I'll just kind of leave that alone. Cool. So with that, let me go back to this. Okay. As long as the job, so it probably did so just because, yeah. Alright, so I'm stopping my screen. It's been fun. Thanks for moderating for me. Yeah, guys, please give us feedback. Let me know how I did. Let me know if I, talk too much or if I talk too little. Yeah, all that.